So in the previous video, we talked about the program status word, also referred to as the PSW. It's also sometimes referred to as the flag register itself, right? So PSW actually stores multiple pieces of information about the currently executing instruction. So it stores multiple flags or bits of information about the currently executing instruction. So whatever instruction is now being executed as part of my either using the control unit or the ALU, right? So some information about that currently executing instruction is stored in the PSW. Now PSW itself has multiple flags. Again, in whole of digital logic design and in computer organization, a flag is, you can think of flag as a bit, right? A flag can either be set or unset, right? Flag being set basically means this bit is set to 1. Flag being reset. So this is what is called as setting a flag, right? This basically means resetting a flag, right? So a flag basically represents or constitutes one bit of information that you can either set or reset. Okay. So this terminology, setting a flag and resetting a flag, is used to represent one bit being made value equals to 1 or 0. So the program status word itself, remember it has the name word, right? It basically means it's one word, or it's literally one register which is of length 1 word, typically, right? And it has multiple bits or multiple flags that are part of the PSW, which inform us about multiple things or multiple properties of the currently executing instruction. For example, again, we'll use 8086 and 8085 as an example in most of these instances. So broadly, the PSW consists of conditional flags and control flags, right? So we'll learn about each of these flags in lots of detail in this video and in the next video, right? So the conditional flags, there are basically these 6 very popular conditional flags that exist in 8086 microprocessor, right? So in the 8085 microprocessor, remember 8085 microprocessor is an 8-bit microprocessor where one word equals to 1 byte. So in the program status word, which is 1 word or 1 byte long, you may not have all of these flags. For example, here it has the sign flag, right? It has the 0 flag. It has the auxiliary carry flag. It has the parity flag. It has the carry flag. It doesn't have the overflow flag in 8085 microprocessor. In 8086 microprocessor, remember 8086 is a 16-bit microprocessor. It's a 16-bit microprocessor, which means its one word is 16 bits, right? So the program status word is also 16 bits in the case of 8086 microprocessor, which means I can store more flags of information here. So in 8086, I have additional flags. Again, if you look at modern microprocessor like Intel's i3, i5 or i7 or even i9, these microprocessors are far more advanced, and each microprocessor has a different program status word. Each microprocessor has something different. But as I mentioned earlier, since 8085 and 8086 are some of the simplest processors, we will study in the context of 8085-86. But every microprocessor has different flags that it wants to track. Again, these are the most popular types of flags. Again, we have conditional flags and control flags. I'll explain each of these flags in detail with examples so that you understand why these flags are important, right? Again, typically your conditional flags are to do with your operations in ALU. Typically, most conditional flags are set or reset based on operations, based on arithmetic or logical operations, typically. Control flags, not so much. Again, we'll understand each of these 9 flags. Again, these are all the flags that are there in 8086. Okay, 3 control flags and 6 conditional flags, right? So since 8086 is a 16-bit microprocessor with the word length being 16 bits, I can store all 9 of them in the 16 bits. Very simple concept here. Now let's go through each of these flags and understand what they mean and why are they used in the first place. That's very important. Okay, so let's look at the very simple flag. Let's look at the carry flag now, right? Very simple. What does carry in mathematics mean? So imagine if I am let's say adding these two numbers in binary. Okay, what happens? I say 8 plus 7 is 15, 5. I have carry 1 because I have carry 1 here, right? 9 plus 1, 10 plus 2, 12, 2, and I have carry 1 here. this carry is what? Again, this is in decimal addition, right? This is in decimal operations. So the same carry flag I can also use for binary operations, right? So this carry flag is used in the context of unsigned integers, not signed integers. What is an unsigned integer? Suppose if I have 4 bits, what all unsigned integers can I store? I can store from 0 to 2 power 4 minus 1, which means from 0 to 15 I can store. Again, unsigned int basically means all integers are assumed to be positive integers in this context, right? So obviously, right, imagine if I have 4 bits, I can do 0 0 0 0 to 1 1 1 1. In binary, this is equals to 0, this is equals to 15. So I can store numbers between 0 to 15, right? So let's take a simple example of using a 4-bit integer, okay, so that we understand about the carry flag better, right? In the real world, if you are using an 8085 microprocessor, this will not be 4-bit unsigned integers, they will be 8-bit unsigned integers, right? Very simple. If you are using an 8086 microprocessor, again, depending on the implementation, your integers could be 2 bytes long. But just for our understanding purpose, I'll start using only 4-bit unsigned integers, just for simplicity. Now imagine I have two numbers 8 and 5, okay, in decimal. If I want to add them, first 8 will be stored internally as binary. So what is 8 in binary? 1000. I can represent 8 using 4 bits. I can also represent 5 using 4 bits. So 0101. If I add both of them, what do I get? If I add both of them, what do I get? Simple addition. 01 is 1, 00 is 0, 01 is 1, 10 is 1. That's it. So look at this. What do I have now? 8 plus 5 is 1101. Okay. So this value gets stored in your accumulator. Typically, not in all microprocessors. Typically what happens is the arithmetic logic unit takes the binary 8 as input, binary 5 as input. It stores this result typically in the accumulator. Typically in your 8085, 86 type of processors. Now if there is no carry, look at this. Is there any carry here? Carry from this most significant. See, this is called the most significant bit. This is called the least significant bit, right? So from the most significant bit, is there any carry? There is no carry. So the carry flag, so in this case, my accumulator will contain 1101 and my carry flag will be set to 0. Remember, carry is one of the flags, one of the 9 flags in the 8086. Very simple example. On the other hand, let's take a slightly different example. Imagine I have 8 plus 9. What is 8 in binary? 1000. What is 9? 1001. Right? When I add both of them in my ALU, what happens? 0 plus 1 is 1, 0 0 is 0, 0 0 is 0, 1 1 is 0 with a carry of 1. This is my carry. So what happens now? My accumulator, remember, imagine here I'm assuming that my accumulator, all my data is 4-bit only. So now my accumulator can only contain 4 bits. Here I'm only taking 4 bits as an example. In the actual microprocessors, they'll either be 8-bit or 16-bit, in some cases even 32-bit. Right? I'm just taking 4-bit so that it's easy for me to explain you the concept behind it. Now what happens? This is carry. So there is a carry from the most significant bit. So what happens? Your accumulator will have this value and your carry bit is set to 1 now. Carry is often represented using CY. So the very fact that carry bit is set to 1 basically means that this is not the actual result. Because 8 plus 9 is 17, right? I can't store 17 in 4-bit integer, because in 4-bit integers, I can only store values from 0 to 15, right? And again, remember here, everything that I'm doing here is unsigned integer, which means I'm assuming all numbers are positive. We'll look at examples where we'll also work with signed integers. Slightly more complicated concept, but again, fun to learn. We'll learn about the overflow flag, where we'll learn about signed arithmetic. Now what we're doing here is unsigned integer addition, very simply put. So since 17 cannot be stored using 4 bits, I'm storing some result here, but the answer of adding 8 plus 9 is not 1. It is certainly, because what does this mean in binary? In binary, this is 1, but the carry flag is also set to 1, implying that there was a carry from the most significant bit. So the actual answer is not 1, the actual answer is 10001. Okay, so that's what the carry flag basically tells us. Whenever you have arithmetic logical operations that are, or especially arithmetic operations that you are performing on your on the inputs that you have to your ALU, is there a carry from the most significant bit or not? If there is a carry, in this case the carry bit is set to 1. If there is no carry, the carry bit is not set to 0. Is set to 0. Right? Now, why is carry flag important? Because carry flag is informing us that the value in the accumulator is not the complete value. There is one more bit, but I'm not able to store that because my accumulator and all the numbers that I have are only 4-bit. That's why I'm not able to store this information here. Like, this is like storing one more bit of information to say that this number is not complete. There is still one more bit that you have to append to interpret it completely, right? So that's what this implies. Next thing is called as a parity bit. Very, very ingenious actually. So imagine if my accumulator contains this number. Okay, what the parity flag or the parity bit? So now look, count the number of ones. Are the number of ones equal to is an even number? How many ones are there? 1, 2, 3, 4. 4 is an even number. Since 4 is an even number, the parity flag is set to 1. If the number of ones is even. If the number of ones is odd like this, okay, this is one case, this is another case. Imagine if my accumulator is this 1, 2, 3, 4, 5, 6. Okay, even here I have 6, right? So let's do this. So let me just edit this. Okay, imagine if this was one more. Okay, now how many ones do I have? I have 7 ones. So number of ones is odd. So number of ones, I'll use hash to represent number. Okay, so the number of ones is odd here. Since the number of ones is odd, my parity flag is set to 0. Right? If it is odd, it is set to 0. If it is even, it is set to 1. You might wonder, why do we need this? Okay, why do we need to store this information? There is a whole area in computer science and in electronics called as error correcting and error detection codes. Now imagine a world, right, where this is the data that I have in my accumulator and this is what is there in my parity flag. Okay, now let's assume there is a sudden spike in voltage to my circuit board, to my microprocessor. The microprocessor data could get corrupted. This whole thing could get corrupted. These ones and zeros could go haywire. Now, if there is only change in one bit amongst them. So look at this. If instead of this value, there is a sudden electrical spike or there is some error that is introduced into this accumulator value because of some electronic failure, because of whatever failure. Now let's assume this value becomes 1011 1010. Here what happened? Only one bit got flipped. Rest everything stayed the same because of this huge pulse of electricity that was given. Let's assume there is an electrical surge going to my microprocessor, or huge amount of electricity or huge amount of voltage went into my microprocessor. Some corruption of the data happened. Now we can detect that corruption happened very easily. Again, just parity is one of the simplest forms of detecting errors. Now if this value got changed to this, now how many ones are here? 1, 2, 3, 4, 5. So if this is 5, let's assume the parity flag did not get impacted. Let's assume. Then I have 5 ones here, but I have parity flag equals to 1. What does that imply? That implies that this data, either this data is corrupted or the parity flag is corrupted. In such a case, what do? We don't use the data that is there in the accumulator. We reload the data from memory or from disk. Right? That's what we end up doing. So parity flag is used to detect errors, is used to detect if there is any error or if there is any corruption or if there is any modification to the accumulator data without updating the parity flag. Right? So again, this is one of the simplest forms of error detection. Error detection is a very, very interesting area that many electronics and mathematics and computer science students study. It's a huge field onto itself. I know universities which offer error correction and detection courses, especially mathematics departments, electronics departments, computer science departments, as one full-fledged course. Right? What we're touching upon here is a very simple concept. Again, I will not be able to go too deep into error correcting codes because that's a big topic onto itself. But I wanted to give you the gist of the idea here. Right? Next thing is called auxiliary carry. Now let's see, what does auxiliary carry do? So imagine I have 1 byte integers. Okay, imagine I have 1 byte integers. Very simple concept. Now this is my first 4 bits, my second 4 bits, my first 4 bits, my second 4 bits. Right? Now what is this is 4 bits is called a nibble. 4 bits is called as a nibble. Right? 4 bits is called as a nibble. Right? This is called as a lower nibble. This is called as a lower nibble. This is called as the upper nibble, because 4 bits, right? Now auxiliary carry, what it does is, imagine if I'm summing these two up. Again, let's assume these numbers are in hexadecimal. A equals to 10. What is A? A equals to 10 in hexadecimal. A plus 4. What is it? A plus 4 is 14. What is 14 in hexadecimal? A is 10, right? A is 10. So B is 11. So B, C, D, E, F, right? So A is 10, B is 11, C is 12, D is 13, E is 14. So their sum will be equal to E. Look at this, their sum will be equal to E. Now I can represent E using the 4 bits. I can represent E using the 4 bits. Now I'll sum up 2 and 3, I'll get 5. Now there is no carry. Look at this, here auxiliary carry, the way it works is this. If there is a carry from the lower nibble to the higher nibble or the upper nibble, then the auxiliary carry is set to 1. In this case, auxiliary carry is not set to 1. So my accumulator will have this value. My auxiliary carry will be set to 0. Let's take another example. Imagine if I have 2A plus 2A. Let's assume this is what I have. Now when I'm summing these two things, A is 10, A is 10. 10 plus 10 is 20. I cannot represent 20. Look at this. I cannot represent 20 using a single nibble. Because in a single nibble, I can store values from 0 to F. Or in other words, 0 to 15. I can't store 20. So since I can't store 20, I can only store some part of 20. And what do we do? Because we are doing everything in base 16, right? We are doing everything in base 16. 20 minus 16. So I have 4 here and I carry 1 here. I carry 1 here, which means from the lower nibble to the upper nibble or the higher nibble, I've carried something. So what is the final value? 2 plus 2, 4 plus 1, 5. So this is what you will get as the answer finally. But there is a carry from the lower nibble to the upper nibble. The auxiliary carry in this case, so this is my final accumulator value. The auxiliary carry is set to 1. So the auxiliary carry is set if there is a carry. If there exists a carry, from lower nibble, lower nibble to upper nibble. That's what it is. Now you might wonder, why do we need this? See, this is called auxiliary carry. What does auxiliary in English mean? It means additional. We already have carry. Remember, we already have carry, right? This auxiliary carry is like an additional carry which we use. Now you might wonder, why do we need this thing? This seems like an artificial thing that we do not care about. Not exactly. There is a concept called as binary coded decimal arithmetic. Okay. So I'll explain you what this is in a little while. So this is often referred to as BCD arithmetic. If you want to perform BCD arithmetic operations, auxiliary carry is extremely useful. Now what is BCD arithmetic? Let's understand that. So let's understand the basics of BCD arithmetic now, or binary coded decimal. What does the name says? We are coding decimal numbers in binary. That's what this means, right? Decimal basically means base 10. Decimal basically means base 10. For example, let's take a simple example, right? Imagine I have number 26 in base 10. This is in base 10. If I want to write it as a BCD or binary coded arithmetic using 2 bytes. Imagine if I want to use 2 bytes to represent it. The 2 bytes I can use is, I can use this byte to represent 2. What does this represent? This represents 2. This represents 6. So what am I doing here? I'm not representing 26 by converting it into binary. I'm converting 2 into binary, storing it as the first byte. I'm converting 6 into binary again and storing it as a second byte. This is what is called as the BCD representation of 26. Okay, this is not the binary conversion. 26 in base 10, if you write it in base, base 2, right? You have 16, right? So you have 16. So let's write this down, right? You have 16 plus, how do you write this? 16 plus 8 is 24. 24 plus 2, right? So 2 power 0 is 0. 2 power 1 is there. 2 power 2 is not there. 2 power 3 is there. 2 power 4 is there, right? So if I want to convert 26 into binary, this is how I'll convert it. 2 power 0, 2 power 1, 2 power 2, 2 power 3 is 8, 2 power 4 is 16. 16 plus 2 is 18. 18 plus 8 is 26. Yes, perfect. This works out, right? So 26 in base 10 is this in base 2. But in binary coded decimal, I'm using a whole byte to represent 2. I'm using a whole byte to represent 6. This representation where I'm using a whole byte to represent one binary digit is called as unpacked BCD representation. This is called as unpacked BCD representation. But this is wasteful because look at this. In binary, what all numbers do I have? I have from 0 to 9. This I can represent just using 4 bits. Why do I need to use 8 bits for this? So the packed BCD representation says instead of using 8 bits to represent it, it makes lots of logical sense to just use 1 nibble or 4 bits. Look at this. This 2 I can represent using this. This 6 I can represent using this. Right? This is 2, right? This is 2. And this is 6. Similarly, I can represent 27. 2 I can represent it using 1 nibble. So the packed BCD says use only 1 nibble per digit. Use only 1 nibble per digit. 1 nibble per digit. Right? Again, nibble as a concept and auxiliary carry as a flag is extremely useful in binary coded decimal arithmetic. Okay, some processors allow us to do binary coded decimal arithmetic. It has its own advantages and disadvantages both. Okay, so in binary, again, these numbers are in binary. If I add them, I should get a value of 53. I should get a value of 53, right? If I just add these two binary values, what do I get? Now let's see. So we will be using packed BCD representation and not unpacked, because unpacked is wasteful. In unpacked, I'm using a whole byte, 8 bits, and it's not required, because to represent these 0 to 9 values, 4 bits are sufficient. With 4 bits, I can represent 0 to 15. So 0 to 9, I can easily accommodate. If I have 3 bits, I can only do from 0 to 7. I can't do 8 and 9. That's why I need 4 bits here. Very simple. Now where I add it. Imagine if I just add it using a simple binary addition. Now what happens here? Let's see. If I add it here, what happens? 0, 1 is 1. 1, 1 is 0 with a carry 1. 1, 1, 1. 1 carry 1. Right? Very simple. Now this 1 comes here. Now this 0, 0 is 0. 1, 1 is 0. 1 carry here. Again the 1 comes here. Now what is this equivalent to? Look at this. So here what is happening here very importantly is your carry. Your carry is set to 0 because you're not carrying anything out of the most significant bit. This is the value that is there in your accumulator right now. Right? I'm just performing simple addition. Again, this is not equal to 53. Just hang on for a second. Okay. Is my auxiliary carry set to 1 or 0? It's set to 0 because there is no carry from this bit to this bit, or from this nibble to this nibble. There is no carry, or from the 4th bit from the left to the 5th bit, there is no carry. Right? Hence, your auxiliary carry is also set to 0. But here comes a problem. If I try to interpret this, so let's look at this, right? So let me put 0 also here. If I try to interpret this as a binary coded decimal, what is this value now? Look at this. What is this value now? This is 4, right? What is this? This is 2 power 0 is 1, 2 power 1, 2 power 2 is 2, 2 power 3 is 8. This is 11. This is 11. Right? This is 11, right? 1, 1, 0, 1. 2 power 0 is 1, 2 power 1, 2 power 2. Sorry. 4. So 12, 13, not 11. I'm sorry. This should be 13. Sorry. This is 13. Now 13 is not a number in base 10. In base 10 or decimal, you have values only from 0 to 9. Now there is a problem here. I can't translate 4 and 13 to 53. Now how do I fix this? So what we do in your BCD arithmetic, in our BCD arithmetic, what do we do now? The very simple thing that we do here is look at this, your lower nibble is greater than 9. That's what it is, right? If your lower nibble is greater than 9, then add 6 to this. Very simple. Add 6 to this. Everything will set right. Right? Add. So if it is this, just simply add 6 to this. That's what you have to do. So this is what you have, 4 and 13. So let me just erase this 4 and 13. Add 6 to this. Okay. So if I add 6 to this, what happens? 0, 0, 0, 0. What is 6? 0, 1, 1, 0. This is 6. Right? This is 6 in binary. So then add 6 to accumulator. This is very, very important. You have to add 6 if your lower nibble's value is greater than, if lower nibble's value is greater than 9. If I add this, what happens? 1, 0 is 0, 0, 1 is 1, 1, 1 is 0 with a carry 1, right? Now 1, 1 is 0, carry 1. Now 0, 0, 0, 1. So there is 1 here. There is 0, 0, 0 here. There is 1 here. Now read this. What is the upper nibble now? The upper nibble is 5. You get your 5. The lower nibble here is 0, 0, 1, 0. What is 0, 0, 1, 0 now? 0, 0, 1, 0 it has to be 1. I'm sorry. 1 0, sorry, my bad. So I got confused here. 1 and 0. If you add 1 and 0, you should get 1. So 0 0 1 1 is 3. So this is your 5 and this is your 3. You got your 53, right? In your BCD packed representation. So now you might wonder, why are we adding 6 here? Because look at this. When you have 4 bits, it can represent values from 0 to 15. Your decimal is 0 to 9. There is a gap of 6 numbers here. That's why we are adding 6. So what is the rule here? Whenever you're doing BCD arithmetic, look at this. Whenever you're doing BCD arithmetic, let's assume you represented this using BCD packed representation. That's very important. We will assume that we are only using packed representation from now on. Okay, the simple. If you want to add two numbers, two unsigned numbers in this case, okay, you add both of them. When you add both of them, if your lower nibble's value, if your lower nibble is greater than 9, then add 6 to this accumulator. Now when I add 6, what happens? This is very important, right? When I add 6, okay, see, when I add, see, first I got this as a solution, then I'm adding 6. When I'm performing the addition of 6, what happens? There is a carry from the lower nibble to the upper nibble. Look at this. This is my lower nibble, right? This is my lower nibble. This is my upper nibble. There is a carry of 1 from lower nibbles to upper nibbles. Because there is a carry, my auxiliary carry will be set to 1 while adding 6, not while adding these two numbers. While adding 6, it will be set. So this is how we perform binary coded arithmetic. And for binary coded arithmetic, it's very, very important that we have auxiliary carry. It's extremely useful for us because it tells us if there is a carry from the lower bits to the upper bits. Okay, so now let's look at one more example. Imagine if I'm adding 28 and 29. Okay, so what happens here? My 22 is represented like this, 8 is represented like this. This is my 2, this is my 8. This is my 2, this is my 9. When I add them, what do I get? 1, 0, 0, 0. There is a carry. Right? There is a carry from, so what happens here? Your auxiliary carry is set to 1 because there is a carry from the lower nibble to the upper nibble. Right? So then there is 1 here, then there is 0, then there is 1, there is 0. There is a carry here, obviously. I'm just writing all the carries to be clear. Now look at this. Now I have, look, what is the case that is there right now? My lower nibble. Look at this. What is the case that I have? What is the rule that I have to write? My lower nibble is less than 9. My lower nibble is less than 9. This value is 1. And, okay, here I need to write one more case here. My lower nibble is greater than 9 and my auxiliary carry is equals to 0. When these two got added, and I got this result, my lower nibble was greater than 9, but my auxiliary carry was equals to 0 at that time. My auxiliary carry was equals to 0. Here what's happening? My lower nibble is less than 9. This is another case. My lower nibble, which is 1, is less than 9, but my auxiliary carry is set to 1. If this is the case, then what do we do? Even in this case, we simply, if this is true, then add 6. Then add 6. If I add, this is 1, right? If I add 6, what happens? This becomes 7. So plus 6. What is 6? 0, 0, 0, 0, 0, 1, 1, 0. That's what 6 is. So if I add it, what is the resultant that I'll get here? I'll get 0, 1, 0, 1 followed by 0, 1, 1, 1. Now what is this? This is 5. Perfect. This is 7. So the result that I got is now the packed BCD representation of the addition. So what do we do for BCD arithmetic? If it's in a packed form, you simply first add, then you apply these rules. The first rule says, if the lower nibble is greater than 9 and accumulator equals to 0, add 6 to the accumulator. The next rule says, if your lower nibble is less than 9, but accumulator equals to 1, even then add 6. This is the second case, right? Let's look at the third case also now, right? This is very interesting case. 88 and 89, if I want to add them, what happens? This is my 8, this is my 8, 8, 9. If I add them, what happens? 1, 0, 0, 0, there is a carry. So auxiliary carry will be set to 1. Right, so I have 1, 0, 0, 0. There is a carry here. So carry bit is also set to 1 now. Look at this. The carry bit is also set to 1 now. Then look at this. In this case, what happens? Now what do we have to do? Now what it says is very important, right? It says now, see, this carry bit is set to 1. This carry bit, because there is a carry from the most significant bit. There is also auxiliary carry set to 1 because from the lower nibble to upper nibble, we have a carry here. Now this is not equals to 177. Now to do that, what do we have to do? So the case, now the next rule is this. The next rule is, if auxiliary carry is set to 1 and carry is set to 1, right? Very simple. And lower nibble is less than 9. And okay, so let's write it case by case. Okay, I think that's better. Okay, so let me write it case by case. Okay, so if auxiliary carry equals to 1 and my lower nibble is less than 9, then add 6 to your lower nibble. Okay, case 1. Second one, if carry equals to 1, sorry, if carry equals to 1 and upper nibble is also less than 9, right? Upper nibble is also less than 9, then add 6 to upper nibble. Add 6 to upper nibble. Okay, so what does it say? Add 6 to this. What is 6? This is 6. When I add 6 to this, what do I get? 1, 1, 1, 0. Right? When I add 6 to this, because look at this, because my carry is set to 1, my upper nibble is less than 9. So I have to add 6 to this also. When I add 6 to this, what do I get? I get this. Right? So what is my final result now? Look at my final result. My carry is set to 1. What is this? This is equal to 7. This is equal to 7. So what do I have now? I have my binary number. Again, this is my decimal number. This 7 corresponds to this 7. This 7 corresponds to this 7. This 1 corresponds to this carry 1. My carry is still set to 1. Okay, this is the third rule. So whenever we are performing binary coded decimal arithmetic, we convert each of the binary numbers to packed. Remember, we are using packed representation where we are using one nibble per digit. And here, remember, here in my rules, I'm using the auxiliary carry here. Here also I'm using the value of auxiliary carry. Even here I'm using the value of auxiliary carry. Here I'm also using the value of carry. So auxiliary carry is a very useful bit in addition to the carry bit whenever you want to perform operations in binary coded decimal arithmetic, right? So again, I've taken a small detour and explained to you binary coded arithmetic so that you understand the actual true purpose of auxiliary carry itself. I could have just said, okay, this is used in BCD arithmetic, then you don't connect the dots. That's why I've taken these examples to explain you how the BCD arithmetic itself works and how auxiliary carry is useful in designing these rules. Right? In the next video, we'll learn about other important flags, both control flags and conditional flags in the next video.